So this video we're going to follow on from my previous one, and we're going to look specifically at adding distances and also adding displacement so we can see how those two things are different to each other. So let's start off by recapping where we left off at the end of last time, looking at what distance is and what displacement is. And then in the final two questions there, we're going to look at what it looks like when we add scalars together and what we get when we add vectors together. So what I need to do is pause the video. If you're wondering why these random letters are here, these come from the previous video, so it might be worth checking that out if you want to know what that means. So pause the video here, get a scrap piece of paper. Can you write down what is distance and what is displacement? So see if you can articulate what each of those things are. And then what I'd like to do is then go, if we have a mass of 2 kilograms and you add 0.5, what the total mass is, and if you have a force of 50 newtons and you add a force of 100 newtons, what the total force is. So pause it and have a crack at that now. All right, so I'm going to assume that you've done that. So let's take a look at what each of these things are. So distance is the length of the path taken by an object, and it's measured in meters, and it's a scalar quantity, so it just has magnitude, not direction. Whereas displacement is the length and direction from the start point to the end point. So it's a vector because it has a magnitude and it has a direction. So it's a vector quantity. It tells you how do we go from the start to the end. Okay, so this question here is about seeing if you know how scalar addition works. So if we have a mass of 2 kilograms and you add 0.5 to it, the mass is going to be fairly simple. You're going to do 2 plus 0.5 equals 2.5 kilograms, and that is always true for scalar quantities. They do follow these nice addition rules. For this one here, it actually depends on the scenario. So we can't actually give a definitive answer to this. If we go, the resultant force or the overall force will be between 50 newtons will be the smallest it can be, and 150 newtons will be the biggest, but it could be in any direction. So let's have a look at a few examples so we can see how that works. So here, let's apply 100 newtons that way, and we'll apply 50 newtons that way, and the resultant force here will be 100 minus 50 gives you 50 newtons. So that's where that's the smallest the force overall can be comes from. If we take the other scenario like this, where we have 100 newtons and we have 50 newtons, the resultant force here will be 100 plus 50, and that's the biggest the resultant force could be. Now, we could also have a scenario where we have, I don't know, the 100 newtons that way, and we have the 50 newtons that way, and the resultant force will be the square root of the sum of the squares. Let's calculate what that happens to be, why not? 100 squared plus 50 squared, square rooted, and that turns out to be 112 newtons there. So the key thing here is we can say what the range of the overall or resultant force will be, but the resultant force can end up being in any direction, so we can't actually be specific. So the key I'm trying to show you here is how scalar addition is different to vector addition. Scalar addition, we can just add them together. Vector addition, we need to know the direction of these two forces before we can calculate the overall one. And that's going to be the same thing that we are going to see from our distance and displacement. Distance is going to follow these kind of rules. Displacement, which is a vector, is going to follow these kind of rules, and that's why I've stuck these in here. So let's start off by adding distances, which are a scalar quantity, as it says here. So let's say we have an object and it travels 6 meters north it goes 10 meters east and then 4 meters south, like you can see in this diagram here. So if we want to work out how far that object has traveled, it's easy. We just do 6 plus 10 plus 4 gives us 20 meters. So what it says at the bottom here is the distance traveled would always have been 20 meters regardless of the direction of the movement. So let's say, for an example, instead of going 6 meters north, we went 6 meters east. And instead of going 10 meters east, we go 10 meters north. And instead of doing 4 meters south, we do 4 meters west. So this is what our diagram now looks like. But if we add together our distances, we still get 20 meters. So the direction here actually wasn't important at all if we're talking about distance, and that's because it's a scalar quantity. It also doesn't matter which order we added them in. So we could have done the 4 meters west, the 10 meters north, and then the 6 meters east. Would have made no difference if we'd done them in the other order or any order for that matter. So that's scalar maths. Let's now move on to displacements, which is a bit more complex. So that's where we're going to focus most of our time. So because displacement is a vector quantity, the direction of the displacement is important in terms of figuring out the total displacement. So let's take exactly the same scenario. 6 meters north, 10 meters east, and then 4 meters south, shown by this diagram here. So remember, displacement is the length and direction to go from start to end. So that's what you can see represented by this blue arrow here, to go from start to the end. So if we want to figure out what our displacement is, what we're going to do here is we're going to form a right-angled triangle, because if we can work out what the sides of this triangle are, we can then work out what the hypotenuse is. And we can, for good measure, let's say we want to figure out what the angle is as well, because remember, displacement, we need a length and a direction. So first of all, this side on the left-hand side is going to be 6 minus 4, so it's going to be 2 meters. This distance here is 10 meters. So the magnitude of our displacement is going to be found using Pythagoras' theorem. So we do 2 squared plus 10 squared, and that's going to be the square root of 104. So let's quickly type that in, square root of 104, and that's going to be 10.2 meters. So this, incidentally, is the symbol for magnitude, if you see those. Let's say we want to find the direction, so this is where we're going to need to use some trigonometry, and if you want some more details on that, I have made a video on how we do trigonometry in physics, which is in the same playlist. So we know that tan theta, and the reason I've picked tan is because we know the adjacent side and the opposite side, so is equal to 2 over 10, which is equal to 0.2. Which means that theta is equal to, let's take the inverse tan of 0.2, and that's 11.3 degrees there, to the right of vertical. So our overall displacement, 10.2 meters to the right of the vertical there. That would be how we describe the displacement. So next, we're going to look at, well, is the order important? Could we have done 4 meters south, then 10 meters east, and then 6 meters north? Well, this statement says it doesn't matter. So let's actually look at that. So let's do 10 meters east, 6 meters north, and 4 meters south. So you'll see that these are the same instructions, but in a different order. So that's what we can see on the diagram. So let's do the same process. Let's figure out the sides of our triangle. So this is going to be 6 minus 4, so that's still 2. This side there is still 10. So the magnitude of our displacement is still going to be 2 squared plus 10 squared, which if I scroll up here, is 10.2 meters. Now, let's say I give this angle in here. So tan theta is going to be equal to 2 divided by 10. So you can see that that is in fact 0.2, which means that theta is the same. It's 11.3. So you can see that if we do the movements in a different order, that has no effect. So actually, the fact that displacement is a vector, the order is still not important, just like it wasn't in distance. We can still add them together in any order we like. We get the same result. And you can kind of see that from the diagram. You'll see the displacement ends up looking kind of the same in both cases. So that kind of makes sense. However, because displacement is a vector, the direction of movements does affect the overall displacement, even if the lengths are the same. So you can see here, instead of going 10 meters east, we do 6 meters. You see previously 6 meters was north. We're now going 10 meters north instead of 10 meters east, but now we're going 4 meters west instead of 4 meters south. So the lengths are the same, but the directions are different. And you can see if we draw them, you can see straight away it looks different. But let's actually go through the mathematical process. So let's form our right-angled triangle for our displacement. So that is 10 meters. This distance here is 2 meters. And let's call that angle in there theta. So the magnitude of our displacement is still going to be 2 squared plus 10 squared, which is still the square root of 104, and I still can't remember it, so I'm still going to look back. That's annoying. Let's get rid of that, which is 10.2 meters. So you can see in this case, it hasn't changed the magnitude of the displacement, but here we can see that tan theta, we're still going to use that. So opposite is 10 divided by 2. So this actually has changed. So we see the angle is now, let's take the inverse tan of 5. The angle is now 79 degrees to the right of the vertical. So you can see our displacement has been changed by having the directions of our lengths being different. We've actually ended up, in this case, changing the angle of the displacement, but we ended up with it being the same overall. And if we'd put our forces in different directions, we could have changed the size of it as well. So maybe if we'd had 4 meters east instead of 4 meters west, that could have changed the size of it as well. But you can see here, because displacement's a vector, the direction of these movements is important and can change the overall displacement. That's why vectors are different to scalars. So what we're going to do to finish up with is essentially summarize what we found there. So 4 questions to see if we've kind of picked up on some of the deductions we've made so far. So pause the video and have a crack at these questions, and then we'll take a look at what we should get here. So pause it now. Let's do that. Okay, so I'm going to assume you've got answers to each of these 4 questions. Let's see what we should have. So, does the order in which movements occur have any effect on the total distance traveled? No, we saw that it doesn't matter on that. We saw that right at the top. And if you want to see some evidence of that, jump back in the video. Does the direction have any impact on the total distance traveled? No, it doesn't. As long as the lengths are the same, the distance traveled will be the same. So moving on to displacement now, does the order in which the displacements occur affect the overall displacement? No, it doesn't. We can add them in any order we choose. That's fine. Does the direction of the movements have any effect on the overall displacement? Yes. The direction of the lengths can change both the magnitude and the direction of the overall displacement. Okay, and that's something to appreciate with vectors that we don't have to worry about with scalars. Changing the direction of the bits that make up the overall displacement can change the overall displacement, both its magnitude and its direction as well. They can both end up being changed by that, and that's why we need both vectors and scalars. Okay, so that brings us to an end of this video looking at distance and displacement, and we'll pick this up looking at speed versus velocity, which you'll notice is very similar next.